What's up, AP Physics C Mechanics student? Welcome back to our Elegant Physics videos. Today's topic, 2.10 circular motion part 2. So let's jump right in. Now, in previous session, we have linked the position in Cartesian coordinate system to the position in the polar coordinate system. So x, y, and r theta are related now via the constraint equations. X is equal to r cosine theta plus a, y is equal to r sine theta plus b, where r represent the radius of the circle, theta the angle, and a and b are simply the center of the circular path. Now, the velocity, which can be decomposed into two components, the Vx and the Vy, with the magnitude known as the speed, E equals to the square root Vx squared plus Vy squared, can be related to the angular velocity via this equation. The speed is equal to r omega. Now, for the acceleration, which can be decomposed into two components, ax and ay, of a magnitude, acceleration equals the square root of ax squared plus ay squared. Now, for the angular acceleration, they cannot be linked together, or let me say that it can be, but it's hardly to be linked to the polar coordinate system. And this is why we need to introduce a new set of bases, the AC and the AT, where the AC is the centripetal acceleration and the AT is the tangential acceleration. Now we know that the acceleration is the variation of the velocity, and the velocity is considered to be a vector quantity, which means it's associated to direction and magnitude. Now the direction uh, and the magnitude can be varied. To vary the direction, we simply apply the centripetal acceleration. So it's an essential tool in circular motion that allows us to change the direction of the object. And this is what we're going to see in the next sections. Now for the magnitude, and I mean by the magnitude of the velocity, the numerical value, and which is the variation of the magnitude, and this can be changed using the tangential acceleration. Now, the magnitude of the centripetal acceleration is given by AC is equal to v squared over r, where v is the speed of the object and r is the radius of the circular path. And this is directly linked to the position. Now, for the tangential acceleration, simply AT is equal to r times alpha, where alpha is the angular acceleration. Now, since we can write the acceleration in terms of ax and ay, so the vectorial equation for the acceleration can be represented using ax vector plus ay vector. And this is equivalent to say that the vector or the vectorial equation for the acceleration is ac plus at. So we can now describe the acceleration via two different ways. And the first way is we use the bases I and j. In the second way, we use the bases centripetal and tangential. In both cases, to find the magnitude at any moment, we just simply apply the square root ax squared plus ay squared if we are dealing with Cartesian coordinate system. In the polar coordinate system, or let me say in the new basis, the acceleration now, the magnitude of the acceleration now is defined to be the square root of a squared plus at squared, which means that, and this is what we're going to find later, that the AC and the AT always perpendicular to each other. Now, the arc length S is related to the polar coordinate system. So the arc length, it's due to the motion of the object around the circular path. So the object will travel this distance. So the distance is associated with this line. So let's assume this is the distance traveled by the object. This is the initial position. This is the final position. So this is the distance traveled. So we're going to use the notation S instead of D to represent this distance. Now to find this distance, VR and theta, we simply apply S is equal to R times theta, where R is the radius of the circular path, and theta is an angle, the angle that uh, confined between the radius and the initial position, or the line that is passes through the center and the initial position. Now, theta, omega, and alpha are related via derivative, but before I explain that, let me say that in unit 2, or let me say in unit 1, we have defined the velocity and acceleration via the following equations. We know that the velocity is delta x over delta t, and the acceleration is delta v over delta t. And we have defined this velocity to be the average velocity and this acceleration to be the average acceleration. Now, for the instantaneous velocity and instantaneous acceleration, we apply the derivative. So it's dx over dt, and the acceleration now is defined to be the dv over dt. And since in the polar terms or in polar coordinate system, we have defined the angular position, the angular velocity or angular frequency, and the angular acceleration, so all are related to the angle. Now, the omega is defined to be the delta theta over delta t. So this is known as not the linear displacement, this is the angular displacement now. And to understand what does it mean by angular displacement is the difference between the initial angle made by the object and the final angle. So for example, let's assume that the object now has traveled from this location to that location. Now, obviously, the angle made by the object now is bigger. Now, the difference between the final angle and the initial angle is known as the angular displacement. And technically, this angle should be this one. This is the difference between the initial angle and the final angle. So this angle is known as the angular displacement. Now, for the angular acceleration is the change in the angular velocity over time. Now, the unit of the angular velocity is radian per second. The unit of the theta is radian. The unit of alpha is radian per second squared. So again, this is known as the angular position. And when we involve the delta, it becomes angular displacement. This is angular velocity. This is angular acceleration. Now, omega here and alpha are known as the average angular velocity and the average angular acceleration. But what about the instantaneous? To find the instantaneous omega and the instantaneous alpha, which means the instantaneous angular velocity and the instantaneous angular acceleration, we need the derivative. So we change the delta into d, and it becomes d theta over dt, and here it becomes d omega over dt. Now back again to this equation, S is equal r theta. So let's apply the derivative on both sides, and we will get that the derivative of S equals the derivative of r theta. I just apply the derivative on both sides, and what we will get is the following. We know that the derivative of distance over time, let me go back to the definition of speed. The speed is distance over time. So if we apply the derivative on the distance itself, if we divide over time, then we get the speed. But this is the average speed. What if we apply the derivative on the distance now, instead of dividing over time? Apply the derivative with respect to time, then we will get what we call it the instantaneous speed. So technically, this is the derivative over time, the derivative of the distance over time. It will give us the instantaneous speed. What about this side? R is just a constant, so we can split it outside the derivative. And the equation becomes the speed equals r dt times theta, or in other words, the derivative of theta over time with respect to time. And the derivative of the theta with respect to time is the omega. So we can change this by omega. And we get this equation, the speed is equal r omega. Now, which is the relation that we have introduced previously? The speed is equal r omega. What is interest behind this equation is v is the linear speed of a specified point on a disk, and omega is in the angular velocity, which represents how fast an object is rotating. So the first one, the speed, this is the linear speed, which describes how much or how fast an object is moving along a certain distance with respect to time. And the omega here is also speed, but the speed of rotating something. Now, for example, here we have two gears. They are traveling the same distance. So the same distance here, the smaller gear will travel is equal to the same distance the bigger gear is traveled. And how did I know that? Because of the number of the teeth here. If you count the numbers, they are equivalent, which means, and they are identical, which means they are traveling the same and equal distances over time. However, it seems like the red gear is rotating faster than the green one. So same linear speed, but different angular velocity. Now this one Also here, the belt will indicate that the travel distance for the smaller gear and the bigger gear is the same. However, the smaller gear is rotating much faster than the bigger gear, which means we can say that the linear speed is the same, but we have different angular velocity. Now here for different point on a disk have different linear speed, but the same angular speed. And let me explain why this is could be true. If we freeze this picture, then and then we locate this three dots on the disk, and then we play the video again, then we pause it in different location, you will feel like the 3 points are aligned all the time together. So if this three dots has moved or have moved to the right, to rotate to the right, they will appear all the time in alignment, which means they will have the same rotation, or they will rotate in the same speed, which means they will have the same omega. But what about the speed? Now, according to this equation, the speed is directly proportional to r. So for bigger r, we will be able to measure bigger speed. Now, r is defined to be the distance between the location of the object and the center of the disk. So here, this is the first r, which is relatively smaller than this r, which is the distance between the second dot and the center. And finally, for the farthest one, the radius is bigger. And the last point will appear to have the highest speed because the radius there is bigger, much bigger. Now, object in circular motion admits centripetal and tangential acceleration. Centripetal acceleration is due to variation in direction of velocity, and the tangential acceleration is due to the variation in the magnitude of the velocity. Now let's focus more on the centripetal acceleration and tangential acceleration. So for the centripetal acceleration, we have to find the magnitude of this acceleration to be v squared over r. Now this kind of acceleration is always exists in circular motion. And the reason for that is we have continuous change of the direction of the velocity. So the velocity has different directions during the motion. So for this satellite, the motion is in this way. So this is counterclockwise direction. So for example, when the object reaches this location, the velocity vector always tangent to the path. So this is the velocity vector, and the acceleration will be directed toward the center. What about this point? If we complete it, the velocity is always tangent to the path, and the acceleration is toward the center. So for example, if you compare this direction and that direction, you will find them different. So at every single point, we'll be able to indicate a new direction for the velocity. And remember that always the velocity will be tangent to the path. And due to this fact, once can say that the centripetal acceleration is always involved in the centripetal and the circular motion, because this acceleration is responsible to change the direction of the object. Now, the centripetal force is defined to be mv squared over r. Now, simply, this is just a Newton's second law because v squared over r is the AC. So mainly we have m AC. It's the force. But a Newton's second law now is promoted to the centripetal level because here we are dealing with circular motion. So this becomes centripetal force, and the acceleration becomes centripetal acceleration in any circular motion. Now this force, according to this factorial equation, it has the same direction as the centripetal acceleration. So this is actually what we found in Newton's second law. F net is always pointing toward the direction that the acceleration pointing to. So F net and acceleration have the same direction, as well as the centripetal force and the centripetal acceleration will be pointing to the same direction, which means in this scenario, the force will be acting toward the center. Now, as the required magnitude, so this magnitude, the mv squared over r, is the necessary magnitude of the unbalanced forces along the center to keep, so the forces here are unbalanced, to keep the object in a circular path of radius r. So one can ask why the object keep rotating around the circle. Is there any kind of force that keep the object in this path? And the answer is yes. This force is promoted to be centripetal force, and this force is a collection. It can be collection of forces, and these forces are unbalanced. This is the relation between these forces. So it can be one force, it can be more than one force, but the thing is, this force should be always directed toward the center in uniform circular motion. Now, notes and misconceptions. The centripetal force is not one force, it's not a force. Then we don't ever represent it in free body diagram. So we don't involve the FC itself in the free body diagram. In the free body diagram, we use the classical forces, the contact and non-contact forces, but we never do that for the centripetal force. The centripetal force is not a force, but rather the direction of the force is acting inward along the center. So it's a collection of forces, or you can say this is the net force along the center. Now, in circular motion, several forces might be acting on the object. If the motion is uniform circular motion, then the net force is said to be only the centripetal force, must have a direction only toward the center. So let's dive deeper in this idea now. The scenarios that we may encounter with are four scenarios in this course. So the first scenario is when we rotate an object attached to a string. The centripetal force here in this case, it will be the tension force, and it will be represented in this way. However, I didn't, as you can notice here, I didn't represent it as FC. So I use the classical way. This is called FT, so the tension force, and we never write it as FC. Now, what about this case? This case is a turning car. So whenever we have an object on a rough surface, it will be experiencing frictional force. So the frictional force here in this case, it will be the centripetal force, the force that keep the object rotating around the circle and is directed toward the center. So the direction of the friction will be toward the center whenever we have this case. Now, for in the outer space between planets, one of planet is orbiting the sun or the Earth or whatever the case is, then the centripetal force here, it will be gravity and it's always toward the center. The last case, going through a loop on a roller coaster. Now here, we don't have one singular force like the other or the previous cases. Here, we have two forces acting on the object. The first force is due to the drag, which is the normal push. The second force is the force of gravity. The net force here, due to these two forces, is the centripetal force. So it's the net force, which is a composition of the gravity and normal push, and we should represent them both in the free body diagram. Now, let's practice more in determining the direction of the velocity and the direction of the centripetal acceleration. Now, let's assume that we have car here, and this car is rotating around the circular path. The direction of the motion here is clockwise, and the target here is to describe the direction of the velocity and the acceleration in the following point, this point, this point, this point, and that point. So let's start with the first point, the direction of the velocity. Remember that the direction of velocity will indicate the direction of motion, and it should always tangent to the path, which means the velocity will be in this way, and the acceleration here in circular motion, if the motion is uniform, then the centripetal acceleration is toward the center. Now, what about the second point, the velocity tangent to the path, and it will indicate the direction of motion. The direction of motion at this point is downward, and of course, the centripetal acceleration, it will be inward. And for the bottom point, the direction of the velocity will be to the left, assuming that the rotation here is clockwise, and the direction of the acceleration will be inward. What about the last point? It will be the velocity upward, tangent to the path, and the acceleration will be toward the center. Now, question one, a person is riding a distance r from the center of rotating platform, as shown in figure one. Usually we call this figure the Sauder view. The person is moving with constant linear speed. Now, for the view looking down on the person, this is the top view, and we're gonna answer the question based on this figure. The same scenario, but from different perspective. Which of the following best shows the direction of the net force So they ask us to find the direction of the net force, and mainly they are meaning by that the centripetal force exerted by the platform on the person or on the person. Okay, so we are having here the person, the velocity is tangent to the path because the path here is this one, and the center of this path will be here, indicated exactly here. We know that the centripetal acceleration and the centripetal force will be always in constant speed pointing toward the center. So this is the direction of the centripetal force and the direction of the centripetal acceleration. Now the direction of the centripetal force is representing the net force, and it's pointing to the right, which means B is the correct answer. Now let's focus more on one of the very repetitive scenarios in AP exams. In the rotating desk, a block of mass M is placed on a disk rotating at a constant speed V. Here we are assuming that the disk has a rough surface, and the block appears to be at rest with respect to the disk. So only the disk is rotating, and due to this rotation, the block will rotate with the same speed, and it appears to be at rest with respect to the disk. But for another observer, not on the disk, it will appear that the block with the disk are forming one body and they are rotating in this way with the same speed. Now, the aim of this section is to determine the maximum distance from the center at which we can place the block and does not slip. And I mean by does not slip that it is not moving outward. So there is no any motion outward. It will remain at this region. So it's moving in this highlighted line, along this highlighted line. Now, since we have a friction here, so the friction is promoted to be the centripetal force, and this is the force that's responsible to maintain the object in this circular path. The block can be placed at a specific point on the disk without slipping out of the rim. Now, here we assume the direction of tendency of slipping is away from the center. So this object has the ability or the tendency to slip away from the center, and the friction is acting in opposite way to maintain the object in this location. So if we rotate the disk with a higher speed, this object may slip away from the center. And this is directly related to the radius, and I will explain why in a moment. Now, suppose we place the block at a point such that it does not slip and moves with the same speed of the disk. Now, the forces acting on the block are three forces here. The first force is the force of gravity, it's acting downward. The second force, we have a surface, so we have normal push upward. And the last force is the inward force, which is the friction. And we have explained that this friction will be pointing toward the center. Now, the thing is, this kind of friction is a static friction because the object is not moving or making any motion on the disk itself. So there is no uh, any relative motion between the disk and the block. This is why we're going to use the static friction and not the kinetic friction. However, the static friction here is toward the center. Then the force that causes the circular motion is the static friction. We say that the static friction is the centripetal force and should be equal to mv squared over r, which is the magnitude required to keep the block in this motion. Now, the thing is, we need to apply the projection along the vertical and along the radial direction. I mean by the radial direction, this direction. Now, vertically, the two forces, Fn and Fg, are equal. They are balance forces, so Fn is equal Fg. Now, unpack the Fg, you will get Fn is equal mg. And along the center, we have only one singular force, and this force is the friction. And we said that this friction is promoted to be centripetal force, which means we can equate it with mv squared over r, especially that Fc is equal m acceleration. Fc here is the friction, and the acceleration is v squared over r in circular motion. Now here we cannot apply directly the relationship F is equaling u as Fn, unless if the case is at the edge of the slipping. So suppose the block is moved away from the center till we reach the state of the edge of the slipping. which means now we have the maximum possible value of the friction. So, which means we can use this formula, because if we didn't do that, then we cannot apply FF is equal mu SFN. Remember that the FF, it has a range of values. These values are between 0 and mu SFN. So this FF, it can be less or equal mu SFN. It can be equal to the FF mu SFN only if we are at the edge of the motion. So FF is equal mv squared over r. Now we can use mu SFN is equal mv squared over r. And remember that the Fn is equal mg. So let's use this fact. Mu s is equal mg, which is equal mv squared over r. Now we can cancel mass with mass. And we just need to rearrange this equation because we are looking for the maximum distance away from the center where we can use or place the block at it. So here the mu s times g is equal v squared over r. If we crisscross, then mu s gr is equal v squared. Since we are looking for the maximum radius or the maximum distance, then the r is equal v squared over mu sg. Then the maximum radius r in which can place the block without slipping is r is equal v squared over mu sg. In other words, we need to know what is the speed of the disk in order to calculate the maximum radius that we can place the object on it or away from the center without making the object to slip away from the circular path. So, for example, let's say that the maximum radius is here. So one can place the block at any point here in this range without making this block to slip away. But once we exceed this distance, for example, here, then the object will slip away from the disk because the friction is no more enough to keep the object in the circle and on the disk or in the circular path. Now, if the speed of the disk increases, this requires more static friction to keep the block attached to the disk according to this equation. So the FF equals mv squared over r. More speed means we need to apply more frictional force to keep the object on the disk. And this is because as the speed increases, then the required magnitude of mv squared over r to keep the block in a circular motion would increase. Now, mv squared over r can be expressed as, let me remind you that the V equals R omega. This is what we found yesterday or in the previous session and in this session. Now, if we replace V here with R omega, we will get R omega to the power 2. Now, let's apply the power 2 on R and omega. Don't forget you have mass here. Now, remember, this is the centripetal force equation. Fc is equal mv squared over R. Now, R omega to the power 2, let's distribute the square on omega and R, and we'll get mr squared omega squared over R. We cancel R with R, and we'll have here survived R, which means the final equation, it would be mr omega squared. Why did I do this? To get this conclusion, if we place the block at a greater distance from the center, this requires more static friction to keep the block attached to the disk. According to this equation, then since this equation represents just the force, so Fc is equal now mr omega squared. Now Fc here, which is the frictional force, or it can be the tension force, when we have greater radius, then we will need to apply more force to keep the object in the circular path. Now, and this is because as the radius increases, then required magnitude mr omega squared to keep the block in circular motion will increase. Prerequisite knowledge. Often problems in physics require prerequisite knowledge. Here we introduce some ideas related to circular motion. So here we have a block on a smooth surface. This block is attached to the spring. Now the tension here represent or can be promoted to the centripetal force. So remember that the tension is given by Kx. And this law is governed by Hooke's law, or this spring is governed by Hooke's law. If the spring is a Hookean spring, then we can apply this formula. Now, The tension in the spring governs Hooke's law, T is equal K times X, causes the centripetal motion, and it will be equated by mv squared over r. So we just simply write Fc is equal MAC. The Fc now is the tension or the spring force. And now we can write it safely that Kx equals mv squared over r. Now K is the stiffness, or sometimes they call it as a spring constant. The unit of the spring constant is a Newton per meter. Now the X is known as the compression amount of compression or amount of stretching of the spring. And it will be expressed in meter. Now a block rotated by a string on a frictionless table again, the tension in the spring now is the centripetal force. So the spring now is replaced with a string. The string will generate a tension force. This tension force, in the absence of friction, it will be our centripetal force, and the centripetal force is equal to mv squared over r. So let's practice. Now a car is traveling clockwise around a circular race track of a radius 1440 meter when the car is at the northernmost point on the circle. So here the object is actually located here at the beginning as shown above. It has a speed 36 meter per second. This is the radius of the track. And slowing down, this is the acceleration, which is 1.2 meter per second squared. What will be the direction of velocity? To find the direction of velocity, we don't need to calculate. We know that the velocity will indicate the direction of motion. And the direction of motion here, at this particular case, it will be to the right. To draw the velocity, we just need a point to draw because the velocity will make a tangent with this point on a circle. And it's acting to the right. Now, according to the compass direction here, right represent the east. So the direction will be due to east. The spring has a force of constant 100 Newton per meter. So this is represent K. And unstretched length 0.07. So this is the initial length of the spring. One end is attached to a post with a free rotate in the center of a smooth table. So there is no friction involved here. And this is the top view. Remember that the side view will appear like this. And it will start to rotate in this way. But this is top view. This is different perspective. Now the other end is attached to 1 kilogram disc. This is the disc with 1 kilogram in uniform circular motion, which stretch the spring by 0.03 meter. So this is the amount of stretching, which means this is the X. Friction is negligible. What is the centripetal force? We know that in this case, the centripetal force will be the spring force or the tension force. Now, the spring force is promoted to be the centripetal force, and the centripetal force, the Fc or the tension, will be written as mv squared over r. However, we don't have direct access on the speed of the object in this case. Our target is simple, to find the Fs. Now, we know that the Fs in general written as K times X, so no need to use the Newton's second law to calculate Fs, since we have direct access to the K and X at this scenario, or in this scenario. So K is 100, X is given by 0.03. Make sure that all of these given data are expressed in the SI unit, and yes, 100 Newton per meter is the SI unit of K, 0.03 is the SI unit of the X, and the final answer will be 3 Newton. So the centripetal force is a 3 Newton. The maximum mass that can be hung vertically from string without breaking the string is 10 kilograms. So this is the maximum mass that we can use in spring or in string without cutting the string. Now, it's better to turn this information into force. Now, the force that will involve here in the scenario is the force of gravity. So let's find out how much force requires without breaking the string. Now, the force is m times g. Now the mass is 10, the G usually we take it as 10, so the answer is 100 Newton. So it's not necessary to be gravity that makes the string to break. So it can be any force. The maximum force that can be applied on the string, it's going to be 100 Newton, whether it's pulling force, gravity force, whatever the force is. A length of the string is 2 meters, so the length is 2 meters. It's used to rotate 0.5 kilogram object in a circle on a frictionless table. So we have a table here and we use only 2 meter. So this 2 meter, to rotate it on the disk, it represents the radius. So this is 2 meter. Now what will be the maximum speed that the mass can attain under these conditions without the string is breaking? So when I say maximum speed, according to the centripetal force, we can write v squared over r. So maximum speed requires the maximum centripetal force. Now here, the type of the centripetal force is string, is the tension force. So the Ft is mv squared over r. Now, this string is characterized with limit. The limit of this string is the 100 Newton. So we cannot apply a force, whether it's a gravity or tension force, on this string, because after this number, after this value, what will happen to the spring? It will break. So actually, since I need to find the maximum possible speed, I need to plug here the maximum possible force acting on the string. And this maximum possible force can be applied to the string is 100 Newton. So let me write here 100 Newton. The mass that we attach to the string is 0.5. The velocity is unknown and the R is 2 meters. Now, let's rearrange this equation. So the V squared is equal 100 multiplied by 2 over 0.5. Since we are looking for the V, not the V squared, we just take the square root. So 100 times 2 over 0.5, and the answer is 20 meters per second. So one can say that if we want to write the correct expression for the velocity in terms of Ft, we just rearrange this equation. This is not necessary step, but I prefer to explain it. So V squared can be written as Ft r over mass. So if we want the speed from now on in this scenario, we just apply the tension times the radius over the mass. And the correct answer is 20 meters per second, which is D. One end of string is fixed. An object attached to the other end moves in horizontal plane with a uniform circular motion. So again, we have uniform circular motion. The radius of this path is r and the frequency is f. Remember that the frequency is the number of cycles per unit of time, and usually this time is taken as 1 second. So when I say 100 hertz, I mean by that 100 cycles every 1 second. The tension in the string is Fs if both the radius and the frequency are doubled. What will happen to the tension? So first, I need to find the relationship between tension, frequency, and the radius. The tension here is promoted to be the centripetal force, and we know that the centripetal force is mv squared over r. The Fc is the tension. You can write it as Ft. Now, there is no any direct relationship till this moment between frequency and Ft. We have a relation between R and Ft. Remember that the V is attached to R because it's equal to R omega. And omega itself, it's written as 2 pi f. We found this relationship in the previous part, in part 1. So let me substitute 2 pi f here. So V is equal 2 pi r f. This is very, very important relationship that link the linear speed with the frequency. Now let's go back to the original equation because I need to find a direct relationship between Ft and frequency. So let me substitute the new formula of speed here. Ft is equal m squared 2 pi rf over r to the power 2, which is equal m 4 pi squared r squared f squared over r. Now we can cancel r with r, but we still have survived r. So, which means the Ft now can be written as mass times 4 times pi squared times r times F squared. This is the formula that links the tension to the frequency. Now, since we have the word doubled, it indicates for you that you must apply the factor of change, but I cannot apply the factor of change unless I have derived a relationship between the quantities, the different quantities. Now we have this relationship, so let's apply the factor of change. In the factor of change, we replace the constant with 1 and the variable with a factor. Now my constant r, which means the thing that I didn't change during my explanation, I didn't change the mass according to the question. We didn't, 4 is just a constant, pi is just a constant. So all of these highlighted in yellow should be replaced by 1. Now we have changed the r, we doubled the r and we doubled the frequency. So we replace them with the factor of change. The factor of change for both of them is 2. So we replace m by 1, 4 by 1, pi by 1, the r by 1, by 2 now because we have doubled the radius. And for the frequency, we replace it by 2. Don't forget that the frequency with the power of 2. And the answer will be 8, which means my force, after we apply the change, it will increase by 8. So the 8Fs, S here stand for the string force or the tension force. I use the letter T as a subscript for this case. However, you can use S. Now, after we apply the change, then the tension force will increase by 8. And that's it for today's lesson on 2.10 circular motion part 2. Thank you for joining me. See you next time.